Okay, welcome everyone to my continuation of what are my favorite theorems, my very biased collection as usual. Today I would like to tell you about something which has a fancy name, the LKB representation, and it's pretty cool. So it is, well, braids are linear. So there are two papers with essentially the same name. It's not braids are linear. The papers are called braid groups are linear, but I simplified that to braids are linear, and I will explain what it means. This is the LKB representation. This is a short for Lawrence, Kramer, Bigelow. The three people worked on this, and the two papers I just mentioned are by Kramer and Bigelow, and the representation originally was introduced by Lawrence. That's where the name comes from. But it's really great. It's really great, and I will show you some code and all that. So we'll see. So the starting point are braids. Who doesn't like braids? Everyone likes braids. Kind of whatever. So there's just this idea of having a group, and a very simple one, a really geometric group, where the elements are just strings that are aligned in R3. So here R3 is some of my background, and they're lined up on two horizontal lines. Let's say one of them is at height 0, one of them is at height 1, and you just have the strings in between them. Really like if you would play a little string game with your fingers and you have some strings in between them, what you get is a braid. So the strings really just tangle around in free space, and what people usually do is they draw the two-dimensional shadow of that picture, just kind of projecting it to the plane, but remembering with which one goes over and under. And yeah, so braids are pretty cool. They form a group, so you can actually multiply braids if you want. So if you have a braid and you have another braid, you can just stack one of them on top of the other. Let me call one braid B, let me call the other braid C. So you just stack them on top of one of the other. And this defines multiplication. But the multiplication won't be important today. So the important point is there's this three-dimensional object, the kind of string games that you play with your fingers. And yeah, so mathematicians got fascinated by braids in 1800-ish. Braids are obviously, I mean, the finger string games are obviously around for much, much longer. And the mathematical study of braids is kind of really important in many fields of mathematics and beyond. Like you could think of it, if you want, as some particle traveling around in space. And here's another particle, maybe a blue particle, traveling around in space. And they kind of cross, and then there's a whatever green particle traveling around in space. So this picture, that was a configuration space picture, if you want, is kind of relevant for more than just funny mathematics. But of course, we all like funny mathematics, I guess. That's why we are here. And the main question we would like to address is kind of, can we tell whether two braids are the same? And that's not an obvious question at all. So what I mean by that is, are they the same as strings? So if you really would play the game in three-dimensional with your strings, with your fingers, you will know that you can really arrange the braid such that it looks really, really different, but it's still the same configuration of strings. So here's a very, very silly example. So if you have something like this picture, maybe it's not a silly example. Actually, it's a very good example, whatever, prototypical example. So if you have this picture or this picture, these are kind of, you have two strings and you have one in the background that you could just move behind the other two strings. The picture you get looks different, but the braid is the same because, well, we have something in the front and you have something in the background that you just move around. A little bit easier example, maybe if you have this configuration, so you have one strand here and you have, well, it's easier with the fingers. So you have one strand here and you have another strand passing over, then you can, or under, over or under. In this case, you can just pull it free, and this is equal to this one. These are called the braid relations. So let's have a look at a few more braids. So here are 6 different braids. I tell you that they are different, but it's not so easy to check, or it's not so easy to really see. But because how can we prove that they're different? There could be some really crazy rearrangement of strings, and in general, braids can get arbitrarily complicated. So here we have just 3 strands, but imagine you have 5,012 strands and 5,012 crossings, and it gets really, really tangled up. you play this game with your fingers, with the strings and your fingers, you know that they get tangled up quite a lot. So how on earth can we tell that? It looks to me, at least from this outset here, if you just have seen kind of many braid pictures, it's an essentially hopeless question. It looks like there's no really good way. That there will be some way, but certainly there's no really good way to distinguish them. And really, honestly, for braids and for knots, this is really hard. So for braids, turns out to be easy. That's what I'm discussing in this video. But for knots, this is really hard. But knots and braids are essentially the same, as I'm going to show you now in the Mathematica demonstration. Okay, here's a Mathematica demonstration linked in the description. And as you can see, this is also where I got my pictures from. So here's a 4-strand braid, and it's really a 3-dimensional object, kind of tangling of those braids. And you can make it into a knot by connecting the bottom and the top points. So by kind of pulling it around and connecting bottom and top, which this program is supposed to do. So I can turn it around, well, 0.616. That will load a little bit and hopefully it doesn't get too crazy. So it will just connect bottom and top points. So it tries to bend the knot quite a lot and will try to connect bottom and top. Very good. Let's go to 0.8. Again, it will load a little bit. Also, we give it some time to think. Not sure. I think just my Mathematica version is outdated or something. But it's really slow. But it's a great program. So it turns around a little bit more. And there was a process dialog. I already got very scared. And as you can see, it's going to, this one is a nice picture. So it's going to close up in at the end here. So let's go all the way out to 1. And what you will see is actually a knot. So here is the knot by just connecting the bottom and top strings, going from the original picture to here. And I can actually display the knot, so it makes it a little bit nicer. So after rearranging, you will get, if you would do that with really honest strings, what you would get is the following picture, assuming that it loads. There you go. And again, the colors here indicate how things are glued together. That's the point. From every braid, you can get a knot, and distinguishing knots is just known to be super hard. So distinguishing braids is supposed to be super hard as well. At least that's what it's trying to say, right? A braid always gives you a knot by just closing it in this bend the strings around fashion. And yeah, it looks like this is a hopeless problem. So I should just quit here and say goodbye. So we have a problem that we can't solve. But turns out, and this is where this LKB representation comes in, that braids are linear. So that's the following idea. As I said, it goes back to Lawrence, the representation itself, and then Kramer and Bigelow showed the linearity. And it's kind of the following idea. There's a way to associate a matrix to a braid. And that's already fantastic because a matrix is so much easier than a braid. And yeah, and you can check the following. The two braids are the same if and only if the matrices are the same. So you have reduced the problem, which looked very hard to distinguish braids, to checking whether two matrices are the same. And every computer can do that easily. So I won't tell you how to associate the matrix. It looks a little bit ugly. It's not so bad, but I still won't do it. But here you can run Sage code, for example. If you Google Sage and LKB representation, you will find kind of a page explaining it where you can copy the code into the online calculator. And here, for example, I have the braid that goes 1. So the notation here is 1. You do a crossing in the first strand. 2, you do a crossing in the second strand. And 1 again, you do a crossing in the first strand. And you wonder whether this is the same as 2, 1, 2. So 2, you do a crossing in the second strand. 1, you do a crossing in the first strand. And 2, you do a crossing in the second strand. And you wonder whether those two beasts here are the same or not. And it turns out that they are. And the way the program checks that, and you could check that as well if you would like to do it, but matrices are something for programs, is to just write down the associated matrix. And the matrices are the same, as you can see. So it's a matrix with entries in x and y, two variables x and y, over some ground field. And as you can see, the matrices are the same, which verifies by the results of Lawrence, Kramer, Bigelow that the braids are the same. And that works for any type of braid. So for really complicated braid expressions. And this was a major breakthrough about 20 years ago and solved the braid recognition problem. It's really, really fantastic. If you know that language, essentially what this is that the braid group has a faithful representation on a finite dimensional vector space. So finite dimensional vector space is just a finite dimensional vector space, whatever your ground field is. And faithful representation means exactly what is written here. You can distinguish braids by looking at the matrices. And that is so ridiculously fantastic that I need to stress that once more, right? Complicated object, braids on one side, reasonably easy objects, matrices on the other side, and you can translate between the two and solve the recognition problem on matrices, which is fantastic. It really, really is totally amazing. It was a really huge breakthrough, as I said, about 20 years ago. And now you might wonder, well, if you can solve the braid recognition problem and we can go from braids to knots as my very slow, this is actually not my, linked in the description, as the very slow program indicated, I should say that it was probably only very slow because I have some flaw with my Mathematica going on. Anyway, the slow but nice program indicated you can always go from a braid to a knot, and here the braid closing just happens as before, just a little bit drawn easier by just going to the right. But it turns out that knots are still hard because, well, in contrast to this picture, the braids, they are now extra relations when going from knots to braids. They're called the Markov moves. I've indicated them here. So the first one is pretty simple. If you have a braid and you stack a braid on top, then you can just slide one around and put it on the bottom again. So I can just take this one here, slide it around the closure, and it ends up at the bottom. And that's just not possible in the braid group where your strings are fixed. And the other one is kind of a Reidemeister one move. But this really just ruins the recognition property. And recognizing braids is still really, really, recognizing knots is still really, really, really hard. Anyway, so as I said, about 20 years ago, there was this breakthrough, LKB representation, how to recognize braids, which is really, really good. You can ask a machine to do it because essentially it turns a braid into a matrix, and all the properties of the braid are encoded in the matrix, and you just need to compare matrices. But that's breakfast for a machine. Anyway, I hope you enjoyed this video, and I also hope to see you next time.